This flowchart illustrates the overall compiler pipeline. Previous lessons treated this entire system like a black box. Source code went in, and an executable came out. Now we are shifting our perspective to go inside that pipeline and watch exactly what happens at every stage. To do that, we will feed the compiler a single statement: A equals B plus C times D. Every phase of the compiler will process and mutate this exact line of code differently. Tracking one isolated statement through the entire system is the best way to understand how abstract human logic turns into physical machine actions. Phase 1 is lexical analysis. At first glance, the compiler's scanner doesn't understand math or logic. It just sees a raw string of meaningless characters. Its only job right now is to scan that text and group it into recognizable units. Once grouped, the scanner assigns two specific labels to each unit. The actual text, like the letter A or the equal sign, is called a lexeme. The category it belongs to, like identifier or operator, is called a token. The compiler immediately saves these categorized tokens into its memory block, known as the symbol table. This creates a quick reference guide that the system will heavily rely on later. By the end of this phase, the compiler has finished its vocabulary check. It has successfully converted a raw, unstructured sentence into a verified list of known words. Knowing the words isn't enough. The compiler now has to ask, are these tokens arranged in a valid logical order? This brings us to phase 2, syntax analysis. This branching structure is a parse tree. We need it because without a clear structure, our equation has a major ambiguity. A machine reading left to right might try to add B and C before multiplying by D. To fix this, the parser creates a parse tree, building a hierarchy out of the tokens. By pushing the multiplication operation down to a lower foundational branch, the tree automatically enforces mathematical precedence. The machine is forced to evaluate C times D first before it can move up and add B. Even with correct grammar, the logic still has to make sense. Phase 3, semantic analysis, checks the symbol table we made earlier to verify that these variables actually exist. It checks the data types to ensure we aren't accidentally trying to multiply a number by a word. These analysis phases confirm the statement follows every rule of the language, ensuring it is structurally sound before the translation begins. Different computer processors speak different languages, so the compiler doesn't jump straight to machine code. In Phase 4, it generates an intermediate representation, a neutral format that isn't tied to any specific CPU architecture. We call this 3-address code. It operates under a strict rule. Each statement can contain at most one operator. To obey this, the compiler creates temporary variables, storing the result of C times D into a new variable called T1. Look at the original equation. If T1 holds the multiplication, what comes next? The compiler has to add B to that result, creating a second temporary variable, T2. Finally, it assigns T2 to A. Before moving on, Phase 5 looks for ways to work faster. The code optimizer scans the new sequence and strips out redundant steps or unnecessary operations, reducing both memory footprint and execution time. Complex human logic has now been flattened into the absolute simplest, most efficient instructions possible. The code is finally ready for the hardware. In Phase 6, code generation, the compiler completes the translation. It maps our optimized list directly into the specific hardware instructions of the target processor, turning our variables into commands like load, mul, add, and store. Looking at the whole pipeline, we can organize these 6 phases into 2 main blocks. The first 3 phases analyze the source code and make up the front end. The final 3 synthesize the target code, forming the back end. Splitting the work this way means compiler developers don't have to start from scratch for every new device. They can reuse the exact same front-end analysis and simply swap out the back end to generate code for a different processor. Whenever you write a line of code, this is the sequence you should mentally see. Raw characters form into tokens. Tokens build a parse tree. The tree flattens into intermediate steps, which optimize down into assembly commands, and finally execute as binary numbers. Visualizing the mechanics of this internal assembly line allows you to predict how high-level commands will eventually behave on the hardware.